Hello, 8th period calculus. Thanks for tuning in. We're going to quickly talk about our notes for unit 6-6 and our second derivative. So we can use the second derivative to determine a function's concavity. So we'll go ahead and look at our function here, and we can go ahead and summarize when we see that function looking like it's up like a cup in these two scenarios, and we can talk about when we see our function looking like it's down like a frown in these two scenarios. Now here we have our sine function, and we know that that function is going to continue with this pattern from negative to positive infinity. All right, so when we're finding the intervals of concavity and reflection points, for the purposes of this graph, we're just going to talk about on the interval from negative pi all the way up to and including 3 pi. So our positive concavity is going to be this part of the graph here. And that happens because I have my derivative, and again, you can run your ruler along your graph where you can have your derivative is starting negative and it's going positive, it hits 0, and then your derivative is continuing to grow. So when you're looking at your derivative or your slope of your tangent line, let's come up and make some notes on the top of the page of what we know is true. If my derivative value is positive, then that means that my function is increasing. And make sure you pay careful attention to whether you're talking about the function or the derivative. If my derivative value is negative, then that means my original function is decreasing. So we need to pay careful attention whether we're talking about the sign of the derivative and the impact that it has on my function. A positive derivative, increasing function; negative derivative, decreasing function. With this lesson, we're going to be talking about my second derivative. So if I were to take the second derivative of the function, if that second derivative has a positive value, what that means then is my derivative function is increasing. And that's what gives me my positive concavity. If my second derivative function has a negative value, then that means that my first derivative is a decreasing relationship, and that is when I'm down like a frown. So coming back to our sine graph, I have a negative, moving positive, moving more positive, which means that during this part of the graph, I have a positive tangent, and that's when my function is increasing. My second derivative is where I talk about, is my second derivative, the rate of change, positive or negative? And if I'm moving from a negative to a positive story, and then I stop increasing but start decreasing, that's what affects my concavity. So along this graph, if I want to look at where I'm concave up like a cup, that's going to be on the interval of negative pi to 0, and then again from pi to 2 pi. If I want to look at where I'm concave down like a frown, I can say that that's from 0 to pi, x values, of 0 to pi and 2 pi to 3 pi. So this concave up like a cup is my orange, and this down like a frown is my pink. So what we want to do is we want to look at the behavior of both our derivative and our second derivative. If a value is concave up, that means that my derivative value is increasing. My derivative value is getting bigger and bigger and bigger. If my derivative value is increasing, then that means that my second derivative is going to be positive because it has a positive rate of change. During my sections where my graph is concave down, that is because my derivative is decreasing. It's getting smaller, so the rate of change is going to be negative. So if you look at where my derivative value is getting smaller, here I'm positive, but I'm getting smaller and smaller and smaller and smaller till I hit 0. And then I'm getting smaller and smaller and smaller and smaller and smaller until I stop getting smaller, and then I start getting bigger again. So these points of inflection that show where this concavity changes, these are our points of inflection. So at each of these points here is where my concavity changes. So when we talk about our points of inflection, we can call them our inflection points, we're going to talk about what x values they are equal to. So we're not confused about whether we're talking about derivative values or whether we're talking about function values or second derivative values. So we'll just talk about where it happens on the x interview. When x is equal to negative pi, 0, pi, 2 pi, and 3 pi, I have points of inflection. And those inflection points are going to be where my tangent line stops getting bigger, starts getting smaller, stops getting smaller, starts getting bigger, stops getting bigger, and starts getting smaller. So we can see how that happens if I mimic that tangent line. All right, let's talk about some facts about our points of inflection. First of all, we're going to talk about them just as the x value. And we're going to say that that happens where my concavity changes. It's going to be when my derivative, f of x, changes from increasing to decreasing. And the other way around too. Finally, because we have this increasing to decreasing change in my function, I can look at my second derivative value, and I can say when I'm looking at that second derivative value, that's when my second derivative value is equal to 0. We can compare that to the critical points. If you want to come back up here to our notes, our critical points is where our f of x was equal to 0. If I have my f prime of x equal to 0, that's going to be my critical point. When I have my f double prime, or my second derivative, equal to 0, that's going to be my inflection point. So make sure you don't get twisted up in talking about the effect that the derivative sign has on the increasing, decreasing nature of the function. The second derivative sine has on the increasing, decreasing nature of the graph of the derivative. What happens when each of those things is equal to 0? All right, let's take a look at our first example. Find the intervals of concavity for this original function. So the first thing I'm going to do is find the derivative of that function. So I'm going to go ahead and multiply my exponent. That cancels out, so that gives me x to the third minus 12x plus 1. Our power rule, 4 times 1/4 is 1 to the 1 less power. 2 times -6 is 12 to the 1 less power. Here's my my exponent is 1. That's where I get my constant. Derivative of the constant, 0. I'm going to go right ahead and take my second derivative of this function, 3x squared minus 12. If I'm looking for my intervals of concavity, I want to know, where does my second derivative equal 0? That's going to be my points of inflection, and that's going to determine my concavity. So I'm going to set 0 equal to 3x squared minus 12. And then I'm going to come up here, and I'm going to say factor out of 3. And I'm going to say 0 is equal to x squared minus 4. So my 0 is equal to x plus 2 and x minus 2. Therefore, x is going to be equal to -2 and +2. If you're curious why I left this room down here, it's because I want to then make a chart. I want to compare my x value, and I want to take a look at my sine of my f double prime of x. And I'm going to look at each of the intervals from -infinity up to -2. I know at -2, I have an output of 0 for my second derivative, not my function, not my first derivative, my second derivative. Then I'm going to talk about the space from -2 up until my next critical point, which is 2. And then I'm going to talk about what happens after that critical point, or that point of inflection, up to infinity. So now what I can do is find test points within each of these ranges and put that into my function. A shortcut way that you can absolutely use anytime that you want is to grab your graphing calculator and go ahead and add your function in. 3x squared minus 12. If I go to my table of values, I'm not surprised to see a 0 at 2, or at -2 and +2. So now I got to look at the signs of my output. My second derivative is positive. My second derivative is negative between my inflection points. And then my second derivative is positive. So therefore, the sign of my second derivative, come back up here, the sign of my second derivative is positive. That means that my derivative is getting bigger and bigger and bigger, which means that I have a concave up range. So when I go to write my answer, I have positive concavity from -infinity to -2 and from +2 to +infinity. I have negative concavity from -2 to 2 on my graph. Now, something else that you could always do with your graphing calculator or Desmos is go ahead and graph your original function. Take a look at it on the graph and see if you agree. is your graph up like a cup, down like a frown, and then up like a cup? Because it's a positive quartic function, yeah, it should look like that story. All right, let's talk about example number 2. Find the intervals of concavity for the function. So when you go to take your derivative, f prime of h is equal to, now you can do this a couple of different ways. You can multiply this out, or you can do chain rule, doesn't matter. Chain rule says my exponent comes out to x squared minus 5 to the 1 less power times the derivative of what's inside is going to be 4x. So when I go ahead and I simplify that out, that's going to give me 8x times 2x squared minus 5. And if you want to multiply that out even more, you can. But since you know that you're going to be taking the second derivative, maybe you want to set yourself up in a situation that's easiest for you. If you want to call this 16x cubed minus 40x, then when you go to take your second derivative, you can just go ahead and use your product rule, or your power rule, 48x squared minus 40. So now what you're going to be doing is, again, setting that equal to 0, and you're going to be looking at where does my second derivative equal to 0, because when my second derivative is equal to 0, my concavity changes. So I'll go ahead and x squared minus 40. I'll come over here so I have room for my chart. My 40 is equal to 48x squared. X squared is equal to 40 divided by 48. Take the square root of each side. And then I go ahead and I get x is equal to plus or minus the square root of 5/6. Now, here's what I know. I know that that's not in simplified radical form, but at the end of the day, that really doesn't matter because that's not my final answer. What it is it gives me points to check on my interval. So if I'm looking at x and I'm looking at my sign of f double prime of x, I'm going to talk about the intervals of negative infinity up to the opposite of the square root of 5/6. I'm going to talk about the opposite of the square root of 5/6 gives me a second derivative equal to 0. And then I'm going to talk about the interval of negative square root of 5/6 up to, but not including, positive 5/6. And then I'll go ahead and talk about the square root of 5/6. And I already know that that one's 0. And then I have the square root of 5/6 on the interval up to infinity. So again, I can go ahead to my graphing calculator and I can enter in the equation of my second derivative, 48x to the second power minus 40. And when I go to my table of values, I'm looking at positive, negative, positive, but because my inflection points are not whole values, I'm not sure. I want to make sure I'm looking at more than one value. Going to my table set and having my table go up in smaller integrals, maybe 2/10 at a time, then I can go ahead and I can see from negative infinity up to negative 5/6. There's my switch to positive. So I start off at positive, and then I go to negative past my inflection point and I'm back to positive. So when I'm talking about my answers for negative and positive concavity, my positive concavity is going to be from negative infinity up to negative root 5/6 and square root of 5/6 up to infinity. My negative concavity is going to be from negative root 5/6 up to positive root 5/6. All right, so let's talk about the back. Let's go back to these charts and read and think about what we're talking about. So as a review, fill this out with me. If f prime of x is positive, then my original function, is increasing. My output of my original function is getting larger. If f prime of x is negative, if my derivative, the slope of my tangent line, is negative, then my original function is getting smaller, is decreasing. If f prime of x equals 0, that's where I find a critical point. And my critical points are what help determine my mins and my maxes. You're looking at your highs and lows, your minimums and maximums of the original function. Let's talk about my second derivative. If my second derivative is positive, then that means that my derivative is increasing. That's concave up. If my second derivative is negative, then that means that my derivative graph is decreasing down like a frown. If my second derivative is equal to 0, that's an inflection point, and that means it's a change in concavity. The most important part about looking at a lot of these graphs is, are you looking at the graph of the derivative? Are you looking at the graph of the second derivative? Are you looking at the graph of your original function? This is my derivative graph. Because my derivative graph is positive from here to here, that means output is positive. That means my original function is increasing, but that means that the slope of the tangent line of my derivative graph, i.e. my second derivative, is negative. So let's talk about what's going on. And we'll do each section one at a time in a different color. When I'm going from an x value of -4 to an x value of -1, so on the interval of -4 to -1, my derivative graph, the value of my derivative is decreasing. Therefore, my second derivative is negative, which means that my original graph is concave down. Let's talk about this interval. Remember, this is my derivative graph. It is the graph of my derivative, not my original function. But these stories I'm coming up with are about my original function. So from -1 to +1, my derivative graph is increasing. Therefore, my second derivative, the slope of that line, is positive. Therefore, on that interval, it's concave up. As I look here, my derivative graph is decreasing on the interval of 1 to 2. My derivative graph, that derivative value is getting smaller and smaller and smaller and smaller and smaller. It had a slope of 2. Now the original graph has a slope of 1. Now the original graph has a slope of 0. Because that is decreasing, that means that my second derivative, my slope of this tangent line, is negative, which means my original graph is concave down. When I look here at this last interval, from 2 to 3, my derivative graph is increasing. Therefore, my second derivative is positive, and I'm concave up like a cup. So now it becomes important to talk about our inflection points. We can go back and say our inflection points are going to be where the concavity of my original graph changes. It's the concavity of my original graph, f of x, is going to change at the points where my second derivative goes from where my first derivative goes from increasing to decreasing. Concave up, concave down. So my inflection points are at x is equal to -1, 1, and 2. All right, so let's go ahead and talk about this last example. And I want you to pay attention to the fact that you're looking at the graph of the second derivative. So when we're talking about the graph of the second derivative, you're really just talking about whether this is a positive or a negative value. So when we go ahead and we look, we'll do the same thing with our colors. When we look from here to here, from negative infinity up to an x value of -3, our second derivative value is positive. Therefore, it's concave up. My original function is concave up. Now, when I look at this part, my derivative of my derivative, my second derivative, is negative throughout that whole interval. Because really, I'm just talking about, do I have a positive or a negative output value of my second derivative? So from -3 up to +1, my second derivative value is negative. Therefore, I'm concave down like a frown. At this point in the graph, from +1 to 3, my second derivative value is positive. Therefore, I'm concave up. And then finally, this last section here, from an x value of 3 to positive infinity, my second derivative value is negative, therefore I'm concave down. We can talk about our inflection points are located that determine the concavity of the original graph are located at x is equal to -3, 1, and +3, because that's where my second derivative is equal to 0. If it makes it easier for you to talk about things in terms of concave up or down, we can do this. My graph is concave up on the intervals of -∞ to -3 and 1 to 3. My original graph is concave down on the intervals of -3 to 1 and 3 to infinity. What's interesting is we can look at this being some sort of function that's kind of wackadoo when we talk about how many changes in concavity it has for that original function. All right, pause and reflect. How can you use the first derivative to find information about a function's concavity? And how can you use the second derivative to find information about a function's concavity? And when you have your thoughts, I want you to think about whether the value is positive or negative, and whether that means that my graph is increasing or decreasing, and what that means in each of the different conversations between my original function, my derivative function, and my second derivative. I'm looking forward to reading your thoughts. All right, so you should have received your homework 6.6. When you're finding the points of inflection for each function, what you're going to do, your points of inflection are where your second derivative is equal to 0. So you're going to have to take the derivative of each function twice, set it equal to 0, and set up a chart to solve. All right, I hope you enjoy your long weekend, and we'll see you next week.